Alright, everybody. So today's cap asked us to do what was basically the cap from this weekend, except now we have like an incline plane. So we're gonna go ahead and first we'll define all of our numbers in here. So we have a first we'll draw our incline plane. We're supposed to give it a given angle, and I'm gonna give this an angle of 45 degrees. So our incline angle is 45 degrees. We have some box on the incline given at 10 kilograms. We have an external force applied at an angle of x degrees, and I'm going to say along the incline, which means that if this were the incline, I'm applying this force 30 degrees. So remember, when we set our axes for the incline, right, we move them like this. So this is this part is the x-axis. So you can consider my force being applied 30 degrees below the x-axis, which is the incline. If that makes sense. It looks like this. So we also need to define a coefficient of kinetic friction. So I'm going to say use of K is 0.05. So, cool. So far, so good. A, we need to solve for the acceleration of the mass. So we're basically going to do what we've been doing for incline plane problems for the last, forever, right? Which is write out unit force statements. And we need to get we need to get the forces that are acting in the x direction, right? Because we know the forces acting in the x direction, the sum of that will give us our acceleration. All right, but one of the forces we already know is going to be friction. Oh, I should probably define this force. This force is 150 newtons. But we need to define the force of friction. So we have to solve for force normal. So the first thing we're going to do is we're going to write net force in the y direction 0, and net force in the y direction is equal to, well, we draw all of our forces out. We got some gravity, we got normal, we have friction going down the incline, we got an applied force acting at an angle of 30 degrees, and I've got, this force of gravity can be broken apart with a 45 degree angle. Cool. So we have everything up minus everything down, so I have force normal minus force of gravity in the y direction, which would be cosine, because it's adjacent to the angle, minus the y component of the applied force, minus Fa, and that would be sine 30, because it's opposite the angle. We can solve this equation for force normal by moving these to the other side. So we have the force of gravity, cosine 45, plus the force applied, sine 30, is equal to the normal force. Plug in our numbers. We can solve for the normal force. We have Fg, we know that's mass times gravity. Mass is 10, gravity is 9.8. 10 times 9.8 is 98. So we have 98 cosine 45 plus our applied force, which is 150 sine 30 is equal to the normal force. Plug this into our calculator, and we will get a number. 98 cosine 45 plus 150 sine 30. So we have 144.3 is equal to the normal force. Wonderful. What does that do for us? 144.3 newtons. does that do for us? Well, we know that the force of friction is equal to the coefficient of kinetic friction times normal force. So we're just going to plug in our coefficient of kinetic friction, 0.05, and our normal force, which is 144.3. So we have 0.05 times 144.3 newtons.
7.2.
7, is that the number? 7.2? So, okay, so we have that to be 7.2 newtons. Thank you. So now let's write our net force in the x direction statement. Net force in the x direction is going to equal all the forces moving up the incline minus all the forces going down the incline. So the forces moving up the incline, we have our force applied cosine of 30, because it's adjacent, minus the force of gravity sine 45, minus the force of friction. So we plug in some numbers here. We get that our applied force is still 150 cosine 30 minus 10 times 9.8 is still 98. So we have 98 sine 45 minus the force of friction, which is 7.2 is equal to the mass times the acceleration. The mass is 10 kilograms, so we have 10 times our acceleration a. So we go ahead and plug this into our calculator. So we get 150 cosine 30 minus 98 sine 45 minus 7.2, and we get 53.4. So 10a is equal to 53.4 newtons. Divide both sides by 10 kilograms, and we get our acceleration to be 5.34 meters per second squared going up the incline. This is part A. Hopefully, this is very familiar, right? Like these are the type of problems that we've been doing, I want to say, for the better part of a month, even though that might not be exactly true. This has been on, I feel like, the last 2 tests. So this is something that I hope everyone is very solid with, because now all we're going to do is build on top of this. Part B. So,
real quickly.
Yeah, let's go.
So, did we have to define the the acceleration at a time again?
Oh,
so,
no. We found the acceleration. We calculated the acceleration.
So,
I use forces
but
to do that.
the sum of f of x, where it equals the force applied cosine theta minus force of gravity cosine theta minus the force of friction.
Yeah.
That's all equal. That's got to be equivalent to the mass and acceleration
Right.
of the total object.
Right.
So.
Yeah. So we know these forces.
Okay.
Right.
And that's why you set it to 10.
Yeah, because we know that 10 is the mass, because it's equal to mass times acceleration. We know that the mass is 10 kilograms.
Okay.
That's
what
what
I'm make sure that
Yeah.
that's
It's all good. So part B. Part B asks us to identify the forces acting on the box. Hopefully we know that this is force normal, force of gravity, force applied, force friction. 4 forces. We did that basically in part A when we put out our free body diagram. So let's do part C. And part C asks us to, for each force, determine whether the work is positive, negative, or 0. So let's talk about this. So I'm going to do C the same part I do B. So is the work of each of these going to be positive, negative, or 0? Well, let's start with force normal. Is force normal going to be positive, negative, or 0? 0, yeah, that's correct. Why? Because it's acting perpendicular to motion. It's not causing any motion at all. So we know that it has to be zero. What about force gravity? Or the work that gravity does? Is that positive, negative, or zero? Yeah, it's negative. This is different from the last cap, and one of the main things that we're talking about is a main difference, is that in this problem, gravity is acting to push the box down. And so it is doing some work. And in this case, because the box is moving up the incline, which we calculated, we know that the work done by gravity has to be negative. What about the applied force? Positive, negative, or zero? Positive, right. Just for the same reasoning, it's pushing the box up the incline. And that's what's actually causing all of the acceleration of the system in the positive direction. And with friction, positive, negative, zero. Negative. That's a key thing, is that friction, if friction is here, it will always be negative. There is no way that a work done by friction can be positive. If work done by friction is positive, something has gone awry.
And so even like work, whether it's positive or negative, again, has nothing to do with like the relation to the axes. Well, I mean, like obviously force, like normal, like I get that, right. But like in terms of the x-axis,
these have they're with respect to the motion of the object. So when we actually calculate the force, where the work done as the force times the distance times the cosine of theta, we'll go back over here and find what the theta is for each one of these forces as compared to the motion moving up the incline. That's the only thing we care about.
So, and just to reiterate, so if the force were to be pulling it in the negative x direction, it would still be doing, force of friction would still be doing negative work.
Right. Yeah, if we define my computer over there to be like the negative x direction, and I was moving this way, well, friction would be doing negative work on me. Yeah, that's correct. Which is kind of a change from like where we just regularly had forces. That's why like when we do work, we write the equation for work to be equal to the magnitude of the force times the magnitude of the displacement times cosine theta. Because that means we don't care about the direction.
Right. Okay.
This handles the direction with respect to the motion. Make sense? Excellent. All right, let's keep going. D. D is fun. So, with D, we need to determine how far the mass moves at a time t seconds. And then for each force, determine the total work done by each of the forces acting on the mass. Okay? So, the first thing we need to do is say, we need to find time. I'm going to say time is equal to 5 seconds.